Section 14.3 discusses integrated rate laws. So let's just do a little recap. So far we've learned when we see a reaction that's progressing, and let's say we have a reactant, A, being consumed over time. We know it generally looks like this, and if I wanted to find the initial rate, I would take the slope at that point, which is the disappearance, right? I would say the rate is equal to negative 1 over A, the coefficient, times by the change in A over the change in time. And knowing that this is the slope at this point here. And so we would take the negative since it's disappearing, and I would do 1 over A if it had a coefficient that was not equal to 1. So that's one way I can find a rate of a reaction at a given concentration. We also learned that rate laws help us to predict the rate when we have different concentrations. So I say that the rate equals the rate constant K times a reactant A to the X order, and if we had more reactants, it would be like to the B to the Y order, and so on. So that is the rate law. And we use this rate equation initially that we learned to help us to determine the orders by taking the ratio of the rates, and that's known as the method of initial rates. So integrated rate laws, what they do is they help us to know what the concentration of a given reactant is over time. And so it's basically of trying to determine like the function that's happening here. And we can tell it's not linear, it's not going straight down, and it kind of looks like an exponential. And so kind of the goal for this is to find a way for us to make this function linear. So what we're going to do is take the function, taking the rate law, taking both of these equations, the rate law and the equation to calculate rate, set them equal to each other, and try to find a way to learn what the function is with respect to time. And what's ultimately going to happen is we're going to find a way to make this a linear plot. So it's taking this nonlinear function here and making it look like a line. So let's jump into first order reactions. So some rates just depend on one reactant to the first power. So right, those are just first order reactions. We're going to make a few assumptions for all of these that we're going to handle. The first assumption is that we only have one reactant, and the other assumption is that their coefficient for it is equal to 1. So it would just be like A goes to some kind of products. Okay, so we're going to use that to move forward. So we know that for a first order reaction that the rate equals K times A to the first power. We also know, so I'm going to write that down over here. We also know that rate equals the disappearance of A. So negative change in A over change in time. So what we can do is set those two things equal to each other. So we end up getting K times the concentration of A equals negative change in A over change in time. Now what we're going to do moving forward is a little bit of calculus to just prove and get our equation that we ultimately will use. So if you don't know calculus, that's okay. You can just kind of follow along, and I will tell you when the big takeaway is. So what we're going to do is move everything that has A on one side and everything that is not A on the other side. So let's move over this concentration of A over to both sides. So I'll divide it, and then I'm going to multiply by negative delta T to both sides. So then that goes away. So now I have the negative K delta T equals the change in A divided by the concentration of A. So now what we're going to do is integrate. We're going to integrate the left side from time equals 0 to t, and we're going to integrate the right side from the initial concentration of A, so what we started out, to any concentration in the future, moving forward. So on the left, we know that the integral of delta t is just t, so we end up getting negative k times t. And on the right side, the integral of 1 over a is the natural log of a. So we're going to have the natural log of a at any point in time, minus the natural log of the initial concentration of A. So if we move everything with natural log of A, so I'm going to keep this on its own side, and I'm going to move this guy over by adding natural log of the initial concentration. So ultimately the equation we get is the natural log of A equals negative kt plus the natural log of the initial concentration. And like I said, we want something that looks like a line, and this one does look like a line. If I was to, so we know that the equation of a line is, y equals mx plus b. So just looking over here, if I was to take all of the concentrations of A and make them a natural log and plot that versus the time. So normally, like up here, right, we just had regular concentration of A over time. If I took all of those data points and took the natural log of that information, then what I would see was a straight line when I plotted it versus time. So what this tells me is that when I do that and I get a straight line, that the slope is equal to the rate constant, negative of the rate constant, and the intercept will be equal to the natural log of my initial concentration. So plot of the natural log of the concentration versus time will be linear when I have a first order reaction. And the slope is equal to negative k. So the main takeaway is this equation can be used when I have a first order reaction. So let's look at this reaction here. We have conversion of methyl isonitrile, so CH3 and C, going to acetonitrile. So basically the carbon and nitrogen are just switching spots. And this has been determined experimentally to be a first order reaction. And we could tell that because when we plot the pressure versus time, it's nonlinear, which is pretty common. But if I took all of those data points for the pressures and I took the natural log of them and then plotted that over time, we get a very linear plot, and we could find that the rate constant is equal to the negative of the slope. And it's a negative slope, right? It's going down, and so the absolute value of that slope is going to be the rate constant. And so then by doing this, we know it's first order, so I know what the x value here is equal to 1. So then that's our rate law. And again, the value of k can be determined from looking at the slope. So now that I know that this is the case, and natural log of methyl isonitrile is equal to k, negative kt, plus natural log of my initial concentration. Meaning I could predict the concentration, or in this case the pressure, of this compound, this reactant, at any given point in time, because I have an equation that relates the concentration to the time. So I could plug in any of these numbers at any point in time and then figure out what that concentration is. One more thing before we practice is we're going to discuss the half-life of first order reactions. So by definition, the half-life is the amount of time it takes for a half of a reactant to be used up in a chemical reaction. And so there's a couple different ways we could look at it. First, let's look at it graphically. I would look at how much I have at the beginning and half it. So if I start with 150, half is 75. I'm then going to extrapolate over to the curve and then down to the time. And I can see for this reaction, it appears to approximately be about, I don't know, like 13,000 seconds is the half-life. So that's how we could use it graphically. But there is a way that we could determine it mathematically. So we know that we're trying to find the half-life. So we're going to denote that as T1 half. And we know that that happens when our initial concentration, so A naught, is divided by 2. So we're going to plug those variables into our equation. So we're going to take natural log of the initial concentration over 2 equals negative K times the T1 half plus natural log of A naught, which is what I started with. So we're going to isolate T1 half. So first thing to do is move over the initial natural log of our initial concentration over to the other side. And that goes away. And we're going to do some log rules. So when we take and subtract a natural log, what ends up happening is the variable inside the log gets divided. So what happens when this gets simplified is we have natural log of A naught over 2, and then this guy goes on the bottom, A naught. And that equals negative K T1 half. And so the A naughts are going to cancel out. And natural log of 1/2, we could actually flip that over and make it natural log of 2. And then by flipping that over, we have to pull out a negative. So we get negative natural log of 2 equals negative K T1 half. And then the negatives cancel out. And then we divide by K on both sides. And then we get the half-life, equals the natural log of 2 divided by K. So that's how mathematically we can solve for the half-life, or use the rate constant, or use the half-life to get the rate constant. So just FYI, the natural log of 2, if you don't like that, I like it because it helps me to remember that first order reactions, we already know they have a natural log in that function. And so this half-life has a natural log, so I can remember that they go together. But if you want to simplify, you can also say that the half-life equals the natural log of 2 is just a number. It's 0.693, and then we can divide by K. So again, that's just a rounded version of natural log of 2. Now let's practice. So we have the decomposition of dimethyl ether at 510 degrees Celsius is a first order process. When it tells you it's first order, there are obviously a couple things you can do. You can know that the rate is equal to K times that chemical, so dimethyl ether to the first power, we know that. But we also know that the function is going to follow the natural log formula. It tells us the rate constant value, so that's cool, and we have the chemical reaction. It tells us if the initial pressure is 135 torr, what is the pressure after 1420 seconds? So when I see all of that information, I don't see I'm not being asked for the rate at a certain concentration, but rather I'm trying to figure out what the pressure is later on, so at some further time. The only equation that we have that involves time is the integrated rate law. So we're going to write it down, natural log of our chemical here, so CH3 2O equals negative KT plus the natural log of the initial concentration of dimethyl ether. All right, so the key takeaway here was that it told us it was first order, so we knew that we could use this natural log function. So we are given the initial concentration or initial pressure, we're also given a time, and we're given a rate constant. So those all go, here's the rate constant, here's the time, and here's the initial concentration. So let's plug in to that. So we're going to say the natural log of dimethyl ether equals negative K times time, and the units are the same, so we have inverse seconds and seconds, so those will cancel out, plus natural log of that concentration or that pressure, 135 torr. And it's okay that it's in torr, not atmosphere. The units will be the same on both sides, so it shouldn't matter either way. So this is all just one big number. We're just going to plug it in the calculator. I want you to try practicing it. Make sure you get the right answer. All right, so what we'll see is that the natural log of dimethyl ether equals 3.94. So all of those just to get 3.94. Now what we want to do, because we don't want to know the natural log of that pressure, we want to actually know what the pressure is. So to undo a natural log, we're going to take the exponential of it. So we're going to raise it. So e to that number. So if you look at your calculator, near where the natural log is, you'll see e. So you'll just hit e and put in that number. Now that will cancel out the natural log. That's just like how dividing and multiplying are opposites of each other. E and natural log are opposites of each other. So e to the 3.94 gives us a value for our concentration of dimethyl ether, or the pressure, I guess, being 51.4 torr. Okay. So once again, when we're given an initial and we're given a time and a rate constant, that should be starting to give you signals that we're going to use the integrated rate law because it has all of those features. All right, let's look at this other problem here. We have this reaction we saw earlier in an earlier section. It's first order reaction, so that's telling us, right, natural log. And we want to use the figure to estimate the half-life for the reaction and then use the half-life to calculate the rate constant. So graphically, we're going to go over here. We know that we started at 0.1, so half of that is 0.05. So we're going to go down to 0.05. We're going to go and extrapolate down. And it looks like a little less than 350, so let's just call it 340. So let's call our half-life is, and their units are seconds, 340 seconds. All right, so A is done. For B, we're going to use the half-life equation to find K. So we know that the half-life equals natural log of 2 over K. And so we're going to cross-multiply to get the K on top and the half-life on bottom. So we get K equals natural log of 2 over the half-life. So plug those numbers in and put it in a calculator. So natural log of 2 divided by 340, and that gives us 2.04 times 10 to the negative third inverse seconds. Okay, so now we've used first order reaction, integrated rate law. Numerically, we've used the half-life and determined it graphically and rearranged to find the rate constant. Now we're going to move on to second order reactions. So just so you know, if I was to plot concentration versus time of a reactant, and we already looked at okay, they generally go down. When I look at that, I can't tell if it's first or second order. They kind of look similar as far as like their shape. So it could be first, it could be second. And so again, if I was to take this information and plot the natural log of that concentration versus time, if it was linear, then I know it's first order. If it's not, if it doesn't come out linear, if it's a little still got a curve to it, then it's not first order. So we need to try another function to see if that gives us a line. So that leads us into second order. So we already know that when we have a second order reaction, the rate law looks like rate equals K times A to the second power. We're going to, again, still make the assumptions that we have one reactant, just A, and its coefficient is 1. We also know that rate is equal to the negative change in A over change in time, right? That's how we find the initial rate. So again, we're going to set these two things equal to each other. So we're going to get K times A squared equals negative change in A over change in time. We're going to move all of the A parts over, so divide by A squared to both sides. I'm going to multiply by negative delta T to both sides. All right, so that goes away. And so we end up getting negative K delta T equals change in A over, concentration of A squared. So again, we're going to do some calculus. We're going to integrate from 0 to T and integrate from initial concentration to the concentration at any point in time. So on the left-hand side, we again get the same thing, negative KT. And on the right-hand side, the integral of 1 over A squared is going to be negative 1 over A. So we're going to get negative 1 over concentration of A minus negative 1 over concentration of A naught. So those negatives become positives. And we're going to move the 1 over A to the other side and the negative KT to the other side. So we'll get ultimately 1 over A equals positive KT plus 1 over A naught. So once again, we have something that resembles a line where y equals mx plus b. So for second order reactions, when you plot 1 over the concentration versus time, it gives you a straight line. The straight line has a positive slope, and so we could use this to help us to figure out if a reaction is first or second order. A first order reaction would only be linear if we plotted natural log of the concentration versus time, where the second order reaction would be linear if I plotted 1 over the concentration versus time. So let's go on to the next slide. Here we can see this reaction of the decomposition of nitrogen dioxide. When we plot the natural log of that concentration versus time, it's not quite linear. See, it still has a little bit of a slant to it. When you take the concentrations and take the inverse of those values and plot those versus time, we can see it's linear. This is telling us that this is a second order reaction because it's a linear function, and our slope here is equal to the rate constant. We will use a similar method to derive the half-life. So I'm going to plug in K times half-life, and wherever I see concentration, I'm going to put a half of that concentration. So A naught over 2 equals 1 over A naught plus the half-life. I'm going to subtract this guy over to both sides. Okay, so that goes away. Also, when I have 1 over a naught over 2, the 2 actually can flip above. So we'll get 2 divided by a naught minus 1 over a naught equals k times t1/2. So 2 over a naught minus 1 over a naught just gives us 1 over a naught. So this simplifies into 1 over a naught equals k times t1/2. To get the t1/2 by itself, we're going to divide by k. So we end up getting that the half-life for second order reactions is equal to 1 over k times a naught. So what's interesting about this is half-life for second order reactions actually is dependent on how much you start with of that reaction. Where first order reactions, it didn't matter the concentration that you started with, the half-life is the half-life. So that's interesting. And another way that this kind of makes sense for me to remember that this is the second order one is that the concentration is on the bottom. So we have 1 over the concentration of the reactant, and that's similar to the integrated rate law, right, where we'd have 1 over the concentration. So this is the main takeaway for this slide. So in this problem, you're given a time and a concentration. So this is kind of similar to what you would have in an experiment, as you would have the concentration of your reactant over time. So we need to determine, is it first or second order? Now what I don't want you to do on the assignments, because oftentimes what will happen is the first part is just, it says, is this reaction first or second? And it's a multiple choice and you just pick. Don't just guess. Okay, you're gonna need to graph it. So I'm gonna walk you through the graphing process. I want you to open up an empty Google Sheets so you can kind of see how to do it. I want you to practice walking through it. So the hardest part in these for me is just to enter all the data. So let's go, I'm gonna show you the first step. And that's just in Google Sheets, plugging in that data. So I label the first cell as the time and the second cell as the concentration, and I just put in those values. So the second step is, on this side, we're gonna see, if it's first order, we know that the natural log of NO2 would be a straight line. So we needed, on this cell right below C2, you're gonna put an equal sign, and then you're gonna write ln parentheses, and you're gonna click on this cell. So it'll say B2. You'll end your parentheses and you'll hit enter. It's gonna give you a number, and then it might ask you if you wanna autofill. You're gonna say yes. If you say no and then you want to do it later, there will be like a little blue square. You'll click on it and you'll drag it down to the cells you want to copy. So on the next slide, we'll see that we have what it looks like, natural log. It starts to give you a number. You hit enter and it will drag it down. Now we also want to see if it's second order. So we're going to, in slot D, we're going to write 1 over the concentration of NO2. And in the cell, you're going to write equals 1 over, and you're going to click on this cell again, so B2. You can click on it or you can type it. And again, you'll autofill or drag down and get all of that data in there. Okay, so that's what it looks like. 1 over B2, you hit enter and drag it down. All right, once you do this, you're going to want to plot. So you'll want to highlight. First, I'm going to show you how to plot with the original function. So just time versus concentration. So you want to select these two cells. You can click on cell A and then hit the command button and click on cell B. So right here, A and B, and that'll select all of the cells. You'll want to do that in the future when we do our lab because we're going to have a lot of data, not just like 5 data points. So you'll hit Command, hold it down, and hit B, and all of them will select. Then you're gonna go up into your Google Sheets, and you're gonna hit Insert, and then you're gonna hit Chart. So once you do that, so let's go to the next slide, I'll show you what it looks like. All right, so you'll hit that. Sometimes the chart doesn't show up looking like a scatter plot like this. So what you'll want to do in the setup on the right hand side, there you should get a chart editor. The setup, you'll hit chart type, and you'll scroll down to scatter plot. If it's not one of your recommended ones, you'll hit scatter plot. Then what you'll do is you'll go over to customize. So we can see customize over here. You will scroll down to where it says series. You'll click on series, you'll scroll down a little bit more, and you'll see this part right here, trend line. When you click on trend line, it will put a line through your data. We can tell by looking at this, just by the data and this line now, that this plot is not very linear. We can see how linear it is by clicking on this button, show R squared. So the R squared value here tells us how close our function or our data fits to this straight line here. And so it's about 92.7% linear. We're going to be looking for the number that's closest to 1, meaning 100% linear. And so we can't really tell if this is the most linear yet because we need to plot the other ones, which we will do in a minute. But you will also click on label and hit use equation, and that's going to give us the equation of the line. Now we may or may not need to use that here, but when we find the most linear one, we know that the slope is going to be related to the rate constant, and so it'll just be important to have that. All right, so let's now plot the next ones. Okay. Here on the left-hand side, I plotted the natural log of the concentration versus time, and on the right, I plotted 1 over the concentration versus time. Hopefully you're doing this as well so you can see, and your data should look like this. So the R squared value for the natural log versus concentration is 0.982, and the R squared value for the inverse relationship is 1. So this tells me that the 1 over the concentration versus time is the most linear, meaning that our reaction is second order. And another note we'll want to take from this is the slope here, 0.543. That is the rate constant, which we're going to use in a little bit to get to find out some more information, which the second part of the problem is asking for. All right, so we know that it's second order. I'm going to write down the equation. 1 over the concentration of NO2 equals positive K, which was 0.543, times the time, so KT, plus 1 over my initial concentration. Whoops, not of A, but of actually NO2. All right, so now we could use our information because down here it says if the initial concentration of NO2 in a closed vessel is 0.05 molar, what is the concentration of this reactant after 0.5 hours? So a couple things we want to do. We're given an initial concentration, and we're also given a time, and we're trying to find the concentration at that time. So we're going to plug in our information, 1 over our concentration equals 0.543. This was in seconds, though, because we use our time in seconds. So we want to get 0.5 hours into seconds. Oops. So we'll have 1 hour has 60 minutes, and 1 minute has 60 seconds. Some of you might know that 1 hour is 3,600 seconds. That's fine too. So when we do this dimensional analysis, we get 1,800 seconds. And that's what we're going to plug in into our time. And then we're going to plus 1 over my initial concentration, which we have a new initial concentration being 0.05 molar. So plugging that in to the calculator, we get that the 1 over the concentration of NO2 is equal to 997.4. So then what you're going to do to flip all of it over is hit inverse, like that. That's going to flip everything over. So then what we end up getting is that the concentration of NO2 at that point, and you should be able to find that button on your calculator. If not, you just hit 1 over answer, and it will give it to you. The answer is 1.003 times 10 to the -3 molar. Okay, so that is how graphically you could do it. Once you have that function, you can plug in any initial concentration in any time and find out the concentration at that point. The last thing we're going to talk about is zero order reactions. In this case, rate is actually independent of the reaction concentration, or reactant concentration. And that's because it just basically drops down to 0. It just disappears, it goes down. And so the rate for zero order reactions is equal to just K. Because if I was to do A to the 0, it would just go away and be 1 anyway. So we just have rate equals K. And so these are, again, they're already linear as is. And so the integrated rate law for these guys is that the concentration of our reactant is equal to negative KT plus the initial concentration. So we could already see it's a line, y equals mx plus b, where our initial slope is equal to negative of the rate law. And I'm not going to drive it, but the half-life for this is the initial concentration of the reactant divided by 2K. And if you want me to drive it, I can. Okay, here is our summary table. I think this really captures everything. We have the order. So again, for zero order, it's just the rate equals K times A to the 0, which is just K. Our integrated rate law is on its own. There's no function you need to apply to the concentrations. It just is linear. When we plot that, we get that the slope is equal to negative K, and then this is our half-life value. For first order reactions, our rate law is K times A to the first. Our integrated rate law involves a natural log. And then our slope, when we plot the natural log of our concentration versus time, our slope is equal to negative K, and our half-life is equal to the natural log of 2 over K, which is 0.693 over K. For second order reactions, our rate law is K times A squared, and our integrated rate law is we use an inverse function. So when we do inverse of the concentration versus time, our slope is equal to K, and our half-life is equal to 1 over K times my initial concentration. And this is all you have to know about rate. I know it's a lot, and they all build into each other, but now we're going to actually move on to our learning a little bit more about the rate constant and how it is impacted by temperature.